Hello. So, for last 2-3 classes, we have discussed about the problem of dimensionality of the feature vectors. We have seen that in case of pattern recognition, depending upon the complexity of the patterns that we want to classify or we want to recognize, we have to capture different types of features from the patterns. And the number of features in some cases can be very large. It can be 2 features, it can be 3 features, it can be 10 features, it can be 100 features, or it can be even thousands of features. So, we have seen through our analytical analysis that as the dimension of the feature vector increases, the training complexity or the time required to train the classifiers also increases to a large extent. So, it is always better that if we can reduce the feature dimensions. So, we have said, we have discussed earlier that one way to reduce the dimension of the feature vectors is to project the feature vectors into lower dimensional space. And when I project a higher dimensional feature vector onto a lower dimensional space, then there is always a risk that if I have 2 different classes, say omega 1 and omega 2, and in say higher dimensional space, in n dimensional space, if the feature vectors belonging to omega 1 and the feature vectors belonging to omega 2, they are separable. When I reduce the number of dimensions, it is quite possible that in the reduced dimension, the feature vectors will not remain separable anymore. And the other thing is that what should be the best projection directions, or what is the best projection space. So, we have seen that so far as data representation is concerned in a lower dimensional space, the best way of projection is to project the higher dimensional feature vectors onto the eigenvectors as computed from the feature vectors. And we have also seen that if I simply project the higher dimensional feature vectors onto the eigenvectors or onto the eigenspace, then the separability among the feature vectors may be lost. The feature vectors may not be feature vectors belonging to different classes may not remain separable anymore. So, for that we have gone for Fisher's linear discriminator. So, in case of Fisher's linear discriminator, we have seen that we try to maximize the within the between class scatter, and at the same time we try to minimize the within class scatter. That means, when you project the higher dimensional feature vectors onto a lower dimensional space, we try to find out the projection space in such a way that the clusters or the patterns belonging to different classes, they will be as apart as possible, and simultaneously the patterns belonging to the same class, they will be as compact as possible. And that is what we mean by it tries to maximize the between class scatter and it tries to minimize the within class scatter. And accordingly, we have computed different projection directions. So, in the first case, when simply data representation is our aim onto a lower dimensional space, the projection directions are actually the eigenvectors, and this simply eigenvector projecting onto the eigenvector may not maintain the separability. So, which is not very suitable for classification purpose, because in case of classification, it is not only data representation onto the lower dimensional space, but it is also the separability of the data belonging to different classes that is very important. So, for classification, our aim is that we want to find out the projection directions which maximizes the between class scatter and it tries to minimize the within class scatter. So, today we will take up an example, we will try to solve a problem which will illustrate this fact that if I take projection onto an eigenvector, the separability may not be maintained, but if I project onto another space following the Fisher's linear discriminator, the separability of the data may be maintained. So, we are going to have today a tutorial on multiple discriminant analysis. So, we will take a number of feature vectors from two different classes, a set of feature vectors from class omega 1, another set of feature vectors from class omega 2. So, suppose we have been given some feature vectors, let us take them, that feature vectors say 1 2, then 3 5, then say 4 3, then say 5 6, and say 7 5. So, we are considering two dimensional feature vectors. So, suppose these are the 5 feature vectors which belong to class omega 1. So, these are the feature vectors which are taken from class omega 1, and we have another set of feature vectors, say 6 2, let us take 9 4, then say 10 1, then say 12 3, and say 13 6, and say these are the feature vectors which are taken from class omega 2. And we want to find out the projection direction, so that when these feature vectors are projected onto a lower dimensional space, say projected onto a line, we want to find out the direction of the line, so that when these feature vectors are projected onto that line, the separability of the feature vectors between the two classes omega 1 and omega 2, that will be maintained. So, what we want to do is find out the projection direction that maintains separability between the two classes. Okay. And of course, what we will do is, before finding out such a projection direction which maintains the separability, we will find out the best projection direction so far as data representation into a lower dimensional space is concerned, and then we will solve this problem. We will find out the projection direction that will maintain the separability, so that we can compare the performance of the two, so that we can demonstrate that in one case the separability is maintained and in the other case the separability is not maintained. Okay. So, we have these 5 feature vectors from class omega 1, and we have the 5 featured vectors from class omega 2. Right. So, first, if I want to find out the projection direction for best representation, then what we have to do is we have to find out the eigenvectors of the covariance matrix of these data elements. So, let us see how we can find out the covariance matrix first, and from the covariance matrix we have to find out the eigenvector corresponding to the maximum eigenvalue. So, first let us find out the covariance matrix. So, to find out the best projection direction, we have to consider all these feature vectors together, forgetting about their class belongingness. So, we have the feature vectors 1, 2, 3, 5, 4, 3, 5, 6 and 7, 5 from class omega 1 and 6, 2, 9, 4, 10, 1, then 12, 3 and 13, 6. These are the feature vectors from class omega 2, and considering all these feature vectors, I have to find out the covariance matrix. So, to find the covariance matrix, first what I have to do is I have to find out the mean vector mu, and this mean vector is nothing but mean of all these feature vectors. So, when I try to find out the mean of all these feature vectors, I have to find out the mean of the first component. I also have to find out the mean of the second component, and the mean of the first component and mean of the second component, these two taken together gives me the mean vector. So, when I compute mean of all these 10 feature vectors, the first components of all these 10 feature vectors, this mean you can compute, this will come out to be something like say 3.5. And the mean of all this second component of all the 10 feature vectors, that will come out to be something like 3.7. So, this is my mean vector mu. And as you know that when I compute the covariance matrix, the covariance matrix is defined as sigma is equal to expectation value of x minus mu into x minus mu transpose. Okay. Where these x's are the individual feature vectors and this mu is the mean vector. So, I have to compute x minus mu. So, from every feature vector x, I have to subtract the mean vector which is mu. So, when I subtract the mean vector from every feature vector, what I have is, let me put here, I will put x minus mu for individual feature vectors. Okay. So, I will put x minus mu here. So, here you find that when I subtract this mean vector mu from the first feature vector which is 1, 2, this will simply be minus 2.5 minus 0.3. So, this is the first feature vector minus the mean vector. For the second feature vector, it will be minus 0.5 and 1.3. For the third vector, it will be 0.5 and minus 0.7. For the fourth vector, it will be 1.5 and this will be 2.3. For this vector, it will be 3.5 and 1.3. So, these are x minus mu for all the feature vectors belonging to class omega 1. Now, coming to the other set of feature vectors, this is 6 minus 3.5, which will be 2.5, and 2 minus 3.7, that will be minus 1.7. Similarly, for this it is 9 minus 3.5, which will be 5.5, and this is 4 minus 3.7, which is 0.3. Similarly, for this it will be 10 minus 3.5, which is 6.5, and 1 minus 3.7, this is minus 2.7. For this vector, it will be 12 minus 3.5, which will be 8.5, and this is 3 minus 3.7, obviously it is minus 0.7, and for the last one it will be 9.5 and 2.3. So, these two rows actually gives me the feature vectors x minus mu, where x minus mu have been computed by subtracting the mean vector from the individual vectors. And then for each of these vectors, after subtraction of the mean vector, I have to compute the x minus mu into x minus mu transpose. And then I have to take the average of all those matrices which I get, that gives me the expectation value of x minus mu into x minus mu transpose, which is nothing but my covariance matrix. So, if I do that for the first one, you find that the first one is minus 2.5 and minus 0.3. So, what I have to compute is minus 2.5 minus 0.3, this is my x minus mu, and x minus mu transpose will be minus 2.5 minus 0.3. So, this is a column vector which is of dimension 2 by 1, and this is a row vector of dimension 1 by 2. Obviously, I can do matrix multiplication, and the product matrix, the resultant matrix, will be of dimension 2 by 2. And if I simply compute this, you find that the value of this matrix will be 6.25, 0.75, 0.75, and then 0.09. So, this is one of the matrices. Similarly, for the second one, which is minus 0.5, 1.3, 0.5, 1.3, when I do this multiplication, this matrix would be 0.25 minus 0.65 minus 0.65, and this one will be 1.69. For the third one, which is 0.5 minus 0.7 into the row vector 0.5 minus 0.7, this will be simply 0.25 minus 0.35 minus 0.35, and this one will be 0.49. So, this is my third matrix, and this way if I compute all the matrices, once I have said how to compute individual matrices x minus mu into x minus mu transpose, this can be done for all the vectors x minus mu, and I can get similar such matrices. So, as I have 10 different vectors, I will have 10 such matrices. So, let us put those 10 matrices one by one. So, this is my matrix 1 M 1, this is my matrix M 2, this is my matrix M 3, Similarly, M4 with the fourth vector, that will be simply 12, yeah. So, that will be 2.25, 3.45, then 3.45, 5.29, M5, the fifth matrix, sorry, let me go to the other page. M5, fifth matrix will be 12.25, 4.55, the sixth matrix M6 will be 6.5 minus 4.25 minus 4.25, 2.89. M7, seventh matrix will be 30.25, 1.65, 1.65, 0.09. M8 will be 42.25 minus 17.55 minus 17.55, 7.29. M9 will be 72.25 minus 5.95 minus 5.95, 0.49. And the last one, M10 will be 90.25, 21.85, 21.85 and 5.29. Right. So, these are the 10 matrices that we have. Okay. So, the first matrix is this, which is x 1 minus mu into x 1 minus mu transpose. The second one, x 2 minus mu into x 2 minus mu transpose, that gives this. Third one, x 3 minus mu into x 3 minus mu transpose, that gives this. The fourth one, x 4 minus mu into x 4 minus mu transpose, that gives this, and continuing this way up to the 10th one, x 10 minus mu into x 10 minus mu transpose, that gives me this. So, I have this total of 10 matrices. Now, out of these 10 matrices, when I combine them, I add them and divide by the number of matrices that I have, what I get is the expectation value. So, as per our definition, the covariance matrix sigma is equal to expectation value of x minus mu into x minus mu transpose, and over here, because we have 10 different vectors, so this expression will simply be 1 upon 10 into summation. So, here I use this symbol for the summation operation. X I is the ith vector minus mu into x I minus mu transpose, where the summation has to be taken over I is equal to 1 to 10, as I have 10 different feature vectors, and accordingly I have 10 different matrices. And each of this x I gives me a matrix Mi, the ones that we have computed here, M1, M2, M3 and so on. So, each of x I minus mu into x I minus mu transpose gives me a matrix Mi. So, this expression will simply be 1 upon 10 into summation of M I varying from 1 to 10. So, effectively what I have to do is I have to add all these 10 matrices M1 to M10. All these different matrices have to be added and then the matrix have to be, the summation matrix have to be divided by 10. And when I do that, you find that this simply becomes 26.275, 0.35, 0.35 and 2.53. So, this is my covariance matrix. So, this is what is the covariance matrix. Now, the next step that I have to do is I have to find out the eigenvector corresponding to the maximum eigenvalue of this covariance matrix. So, first let us try to find out what will be the eigenvalue or the maximum eigenvalue, and then let us try to find out what will be the eigenvector corresponding to that maximum eigenvalue. So, you all know that if lambda is an eigenvalue of this matrix, then I can simply find out the eigenvalue lambda by using this equation that this is 26.275, not 2.275, this is 26.275, then 0.35, 0.35, then 2.53. Okay. So, the equation that I have to use is 26.275 minus lambda, where lambda is an eigenvalue, 0.35, 0.35 and then 2.53 minus lambda. Take this determinant and equate this determinant to 0. Okay. And you solve this equation, I get the values of I get the different eigenvalues lambda. So, simply this equation leads to 26.275 minus lambda into 2.53 minus lambda minus 0.35 square, this is equal to 0, which is reduced to lambda square minus 28.805 lambda plus 66.3532 is equal to 0. So, here you find that I get a quadratic equation in terms of lambda, where lambda is an eigenvalue of the covariance matrix. And as this equation is a quadratic equation, so obviously the lambda will have two solutions, which indicates that this matrix, this covariance matrix will have two eigenvalues, and corresponding to each of these eigenvalues I have one eigenvector. So, this covariance matrix will have two eigenvectors, one corresponding to each eigenvalue. So, when I solve this equation, this is a quadratic equation, the solution is very simple. You can find out that one of the solutions lambda 1 will be 26.28 and the other solution lambda 2 will be 2.525. So, these are the two eigenvalues of my covariance matrix, and out of these two I have to choose that particular eigenvalue which is maximum. So, you find that this eigenvalue lambda 1 which is 26.28, that is the maximum one. So, once I have this maximum eigenvalue, I have to find out what is the eigenvector corresponding to the maximum eigenvalue. And you also know what is this eigenvalue equation, which simply says that if x is an eigenvector of a matrix A is my matrix, and suppose x is the eigenvector, then A x has to be is equal to lambda x, where this lambda is the eigenvalue and x is the eigenvector of matrix A. So, following the same one, here we can find out what is my eigenvectors corresponding to this maximum eigenvalue lambda, which is equal to 26.28. So, let us try to find out the eigenvector corresponding to this maximum eigenvalue. So, in order to do that, we know that our covariance matrix was given by 26.275, 0.35, then 0.35, 2.53. This was my covariance matrix sigma, and if I assume that the eigenvector corresponding to the maximum eigenvalue of this covariance matrix is x, and this being a two dimensional matrix which has got two components x 1 and x 2, right. So, this has to be equal to lambda times x, and where this lambda, the maximum eigenvalue is 26.28. So, this has to be simply 26.28 times x 1 x 2. So, if I reduce these equations into linear equations, I get two equations. One is 26.275 times x 1 plus 0.35 times x 2 is equal to 26.28 x 1, and the other one is 0.35 x 1 plus 2.53 x 2 is equal to 26.28 x 2. So, I get these two simultaneous equations. So, I have to find out the value of x 1 and the value of x 2 by solving these two linear equations, simultaneous equations. And the solution is also very simple, and if you solve this, you will find that I will get x 1 is equal to something around 70 and x 2 will be something around 1. So, that clearly indicates that 71 is the eigenvector of the covariance matrix corresponding to the eigenvalue lambda is equal to 26.28. So, corresponding to this eigenvalue, the eigenvector is 71. And what we have to do is, we have to project the feature vectors which are given onto this vector 71. So, now let us plot these points on a graph paper to see that what kind of projection we get. Right. So, I will use a graph paper to this job. Okay. So, what we have is, let us assume that we have the origin somewhere over here. This is our origin, and I will put these different feature vectors which are given onto this graph paper. And over there, if you remember that we said that these are the feature vectors 1, 2, 3, 5, 4, 3, 5, 6 and 7, 5. These first 5 feature vectors, they belong to class omega 1, and the second 5 feature vectors 6, 2, 9, 4, 10, 1, 12, 3 and 13, 6, they belong to class omega 2. So, when I plot these feature vectors onto my graph paper, I will plot them in 2 different colors. Okay. So, the first one I will use the green color. So, the first one is 1 2, 1 2 that comes somewhere over here, then 3 5, 3 5 is somewhere over here, then 4 3, 4 3 is this, then comes 5 6 over here, and then 7 5, 1 2 3 4 5. Okay. So, these are the feature vectors which belong to class omega 1. Now, let us plot the feature vectors which belong to class omega 2, and I put them into red color. So, the first one is 6 2, you check from here, the feature vectors are 6 2, 9 4, 10 1, 12 3 and 13 6. Okay. So, 6 2, 1 2 3 4 5 6 2. So, this is one feature vector. Okay. Oh, I am sorry. This was 5 6 and the next one was 7 5. 1 2 3 4 5 6 7. So, this one not here, it will come here. Okay. So, 6 2 that comes over here, then we have 9 4, 7 8 9 4. This is another feature vector belonging to class omega 2. Then we have 10 1, this is another feature vector belonging to class omega 2. Then we have 12 3, this is another feature vector belonging to class omega 2, and then we have 13 6 3 3 6, this is another feature vector belonging to class omega 2. Okay. So, these are the feature vectors belonging to 2 different classes, and we have computed that our eigenvector is 71. Okay. What is that one? Anyway, so the eigenvector was 71. So, I want to plot that eigenvector which is 71. So, I 1 2 3 4 5 6 7 71. It will pass through a point somewhere over here. So, I will take a scale to get this direction of this eigenvector, which is this. Okay. So, this is my direction of the eigenvector corresponding to the maximum eigenvalue. And now, if I take perpendicular projection onto this eigenvector, the perpendicular projection of the feature vectors onto this eigenvector, what I will have is the different projections will be like this. This feature vector will be projected here, this feature vector will be projected here, this feature vector will be projected here, okay. So, you find that as we said that all the feature vectors belonging to class omega 1, they are represented by green color, and all the feature vectors belonging to class omega 2, they are represented by red color. Okay. And when I project these feature vectors onto the eigenvector corresponding to the maximum eigenvalue, so these are my projections. Okay. So, here you find that feature vectors belonging to class omega 1, they are projected. So, what we have used is, this is my axis x 1 and this was my axis x 2. Okay. So, the feature vectors belonging to class omega 1, they are projected onto a points in the line which is in this range, and the feature vectors belonging to class omega 2, they are projected over here. So, it clearly says that when I take the projection onto the eigenvector, the projected points, the projected vectors are no more separable. The projections from class omega 1 and the projections from class omega 2, they get intermixed, which is quite obvious in this particular case. Okay. So, the feature vector from class omega 1 is over here, whereas the feature vector from class omega 2 is over here, whereas the rest of the feature vectors which are projected onto the other side, the rest of the feature vectors from class omega 1, they are projected onto the other side. So, I have a mixing of the feature vectors, the projected feature vectors onto a lower dimensional space. Whereas, you can clearly see that I can obviously draw a straight line over here, separating the feature vectors in class omega 2 and the feature vectors belonging to class omega 1 by a linear straight line. So, in our original space, in the two dimensional space, they were linearly separable, but when I take projections onto the eigenvector, they are no more linearly separable, right. So, this is a problem that we face when we project feature vectors from a higher dimensional space onto feature vectors onto a lower dimensional space. And this is the problem which is addressed in the Fisher's linear discriminator, where we try to find out the projection direction which maintains the separability, okay, which tries to maintain the separability by increasing the between class scatter and by decreasing, by minimizing the within class scatter. So, if you remember the Fisher's linear discriminator. So, now let us talk about the Fisher's linear discriminator. So, Fisher's linear discriminator tries to find out the mean of the individual classes. So, it considers the feature vectors belonging to class omega 1 and the feature vectors belonging to class omega 2. Finds out what is the mean of the feature vectors in class omega 1 and what is the mean of the feature vectors in class omega 2. So, one is mu 1, other one is mu 2, and then it computes what is the within class scatter, or what is the scatter of the samples of the feature vectors in class omega 1 and what is the scatter of the samples in class omega 2. Then it defines what is called total within class scatter. So, if you remember, we have said that if S1 is the scatter of the feature vectors in class omega 1 and S2 is the scatter of the feature vectors in class omega 2, then the total within class scatter is given by SW, which is nothing but S1 plus S2. So, this is the total within class scatter. And if mu 1 is the mean of the feature vectors in class omega 1 and mu 2 is the mean of the feature vectors in class omega 2, then when we discussed about the Fisher's linear discriminator, we have said the direction, the projection direction is given by a vector W, which is nothing but S W inverse into mu 1 minus mu 2, where S W is the total within class scatter, mu 1 is the mean of the feature vectors in class omega 1 and mu 2 is the mean of the feature vectors belonging to class omega 2. And this expression was obtained by solving a generalized eigenvalue equation and that eigenvalue equation took care of maximization of the between class scatter. That means, pushing the clusters or the classes as apart as possible and by minimizing the within class scatter, that is S1 or S2, by making those classes as compact as possible. So, we try to make the feature vectors belonging to a single class very compact and simultaneously try to maintain the distance between two different classes. So, accordingly, we had obtained an criteria function, and by optimization of that criteria function, we could come to a solution something like this, which says that the projection direction which maintains the separability is given by S W inverse into mu 1 minus mu 2, where S W is the total within class scatter. So, if I have two different classes, one is S 1, the other one is S 2, S 1 is the scatter of class 1, S 2 is the scatter of class 2. So, total within class scatter S W is given by S 1 plus S 2. So, let us try to see that by using this Fisher's linear discriminator approach, what projection direction we get and how does it differ from the eigen direction. Okay. So, here again I will consider the same set of feature vectors belonging to class omega 1 and omega 2, so that I can compare the performance of projection onto a eigenvector direction onto a eigenvector and the projections onto the Fisher's discriminator. Okay. So, as we said that we have two sets of feature vectors, two dimensional feature vectors, one set taken from class omega 1, the other set taken from class omega 2. So, from class omega 1, the feature vectors we have taken are 1, 2, 3, 5, 4, 3, 5, 6, 7, 5. So, these are the feature vectors which are taken from class omega 1. So, each of them is a two dimensional vector. 1 2 is a vector, 3 5 is a vector, 4 3 is a vector, 5 6 is a vector and 7 5 is a vector. Similarly, I had other set of feature vectors which are 6 2, 9 4, 10, 1, 12, 3 and 13, 6, right. And these are the feature vectors which are taken from class omega 2. So, first what you have to do is we have to compute the mean of the feature vectors from class omega 1 and the mean of the feature vectors from class omega 2. So, here I will compute mu 1 and here I will compute mu 2. So, if you compute the mean of these feature vectors, which is mu 1, you can easily find out that this is 4 plus 4 8, 8 plus 5 13 plus 7 20, 20 divided by 5 as I have 5 different feature vectors. So, the first component will be 4 of mu 1 and similarly sum of these second components divided by 5, that will simply be 4.2. So, mu 1, the mean of the feature vectors belonging to class omega 1 is 4.2. Similarly, mu 2, the mean of the feature vectors belonging to class omega 2, that also I can compute from here. So, mean of the feature vectors belonging to class omega 2, mu 2 will simply be this is 15 plus 10, 25, 37, 50 divided by 5, that will be 10. So, that is the first component, and in the same manner the second component you can compute 3.2. So, this is the mean vector of the feature vectors belonging to class omega 1 and this is the mean vector of the feature vectors belonging to class omega 2. So, once I have these two means, then I have to compute the scatter of the feature vectors belonging to class omega 1 and scatter of the feature vectors belonging to class omega 2. That means, I have to compute what is S 1 and what is S 2. And S 1 is nothing but sum of x I minus mu 1 into x I minus mu 1 transpose for all x I belonging to class omega 1. So, we compute x I minus mu 1 into x I minus mu 1 transpose for all the feature vectors belonging to class omega 1. So, each of them gives me a matrix. So, I will get a number of matrices, and because here I have 5 different feature vectors. So, I will have 5 different matrices. Sum of all those matrices gives me scatter S 1. Similarly, S 2 will be sum of x I minus mu 2 into x I minus mu 2 transpose for all x I. This summation has to be computed for all x I belonging to class omega 2. So, we have to compute these two. Okay. So, let me stop this lecture here. In the next lecture, I will complete this task, this problem, and then we will compare the performance of this and the projection onto the eigenvector. Thank you.